Hi, my name is Ersilia Vaudo. I am an astrophysicist as background, and I work at the European Space Agency since 1991, so more than 30 years. I would like to go straight to the magic of the nuclear energy that has the power of harnessing the atoms, what is inside the microscopic world. We should go back in time to understand really what there is behind nuclear energy and go at the beginning of last century. So we are talking about 1905. That was defined as annus mirabilis. And this is because this year Einstein, publishing 4 papers, was able in few months to completely change our perspective on the universe and the physical world. In a shell, what Einstein was putting on the table in the special relativity is how the behavior of reality changes when we travel at the speed close to the speed of light. Speed of light was clear at that time is a constant in the void and has an unpassable limit. And this changed in the way the perspective that Einstein put not only on space and time, that because of these facts are now linked forever, but also the perspective on mass and energy. It starts from a very simple consideration. We know by experience how difficult it is to push a trolley full of stuff in the supermarket. And more energy we impress to the trolley, and higher will be the speed of the movement. Of course, it depends also how heavy is the trolley. So the relation is very simple. The energy is equal to the mass multiplied for the speed of the trolley square. If we push the trolley, the speed will increase, but there will be a limit. When the speed will be approaching the speed of light, it cannot go beyond that. This means that all the energy we keep putting in pushing the trolley will go somewhere else. And where it goes, it will go in only the other physical element in the equation, meaning the mass. So we have that with the simple reasoning, energy and mass are the same thing, and the exchange rate between energy and mass is just a mathematical factor, and is the speed of light squared. This is extraordinary. We have mass and energy become manifestation of the same reality. And another way to say it is that the energy trapped in a mass can be unleashed, and the other way around, from energy, a mass can appear. We could say that, for instance, if we are able to convert 1 kilogram in energy, we would have the energy to supply 100,000 ohms for years. This is unbelievable, and again, is something that was not so easy to accept at that time. A movement that becomes an object and an attribute that becomes a body. Now, both fission and fusion are nuclear processes by which atoms are altered to create energy, just by using this magic formula of E equal mc squared. But there is a big difference between the two. Simply put, fission is the division of one atom into two, and fusion is the combination of two atoms into a larger one. Very opposing processes, and therefore very, very different. If I can summarize the difference between the two processes, I would say that in fission, we have a heavy nucleus breaking up to form two light ones, and then from these two light ones, we have neutrons generating that will travel with the high speed, and we create a chain effect. In the fusion system, two nucleus combine to form a heavier one. There is no existence of fission in nature, while we experience the nuclear fusion observing our stars in the sun. The combustion process is exactly the magic of E equal mc squared. Nucleus of hydrogenous squeezing and creating helium and some neutrons. And the energy that is unleashed is the amazing energy that our own stars can create. The fission involves a chain reaction, which can also lead to dangerous meltdown. There is no chain reaction involved in fusion. As I said, fission means that heavy nucleus are bombarded with neutrons, and the most used one is uranium-235, while to merge light nuclei in the fusion system, you need very, very, very high temperature and pressures. Now, the nuclear waste, which is one of the major issues here, that are a byproduct of fission, of course, are an environmental challenge, while with fusion, there is practically no nuclear waste. And another important difference is that the raw materials for the fission, which are essentially uranium and plutonium, are very scarce and very costly, while the raw materials with fusion are essentially hydrogen atoms, are very, very easily sourced, and the fusion reaction can really be clean energy. Now, why we don't have then a fusion everywhere at the moment? The problem is that, as said, to achieve a fusion reaction, we really need extremely sophisticated technology, new technologies, like, for instance, magnetic confinement, because we are talking about a plasma that can reach 150,000 degrees, that should be contained, and if it's not contained, it will melt everything around, and a pressure that is able to trigger this fusion reaction, to push the atoms one into the other. And this is a technology that so far is still in the making. Last year, at the end of last year, in 2022, there was the holy grail moment of some nuclear fusion that was reached by physicists in California. Fusion ignition was achieved and was able to produce more energy than the neutrons needed to create the fusion. But this only lasted a billionth of a second. And still, the energy used was not outpowering, outnumbering the number of energy that was used to inject and to ignite this fusion. So there is a lot of research. At the moment, there are more than 30 different fusion energy projects across the world underway. One of the most important is the International Thermonuclear Experimental Reactor, the ITER, which is a joint fusion experiment in France, is an international cooperation that should be able to start fusing atoms in 2025. Still is not defined how this energy, in case we were able to create, will be converted in electricity and with which kind of efficiency. And also Germany is very active in this and is investing enormously now in fusion, as well as UK and China that have their own experimental fusion reactors. The Financial Times published a few weeks ago an article that highlights that the race to develop commercial nuclear fusion power is heating up. And the problem, the difficulty is really in the safety. It's because it's very safe that is very complicated. When we have ignited the fission process, it goes. And it goes meaning that there is a chain effect that allow the process to be alive. But of course, if you lose control, it can become problematic. Fusion instead needs optimal condition to work. And if you change just a little bit this condition, it just turns off. So it's very safe because if something goes wrong, it stops, but is much more complex. We have to think what the the challenge, the technical challenge of bringing and keep a plasma at 150,000 degrees, keep it confined to avoid that it escapes and melt everything, and also to reach sufficient pressure to ensure that the atoms can have a high probability to interact. And also it's not so clear how to transform this energy in electricity, and with which efficiency is still to be seen.